All right, hi everyone. I wanted to shoot a quick video about predicting products given reactants and knowing different types of chemical equations, bonding, and balancing. So kind of a three-step method when you come across problems that they give you in something like exercise 10.2b. So I'm going to do a variety. If you're looking at 10.2b right now, I'm going to do a variety of these problems and kind of wrap it all together so that those of you who don't have 10.2b can still understand how to apply what I'm about to teach you to all three steps of bonding, balancing, and predicting products given any type of question you may have. One of the big things you absolutely need to know, first and foremost, are your 5 different types of chemical reactions. You've got to have those pretty well down, or at least on a piece of paper somewhere close to you. So I'm just going to quickly go over those. Our first type of reaction is combustion. So that's C something, H something. It could be C2H8 or C3H8, C5H, whatever. It doesn't matter. It's just something there. You have carbon and hydrogen. You're always combining that with oxygen, Brinkelhoff. So oxygen is O2 automatically. And you're always going to get water and carbon dioxide out of that. So the balancing when it comes to all this is really just dependent on how many carbons, how many hydrogen you have, because everything else is given to you. So that is combustion. Our second type of chemical equation is something called single replacement. That is something like AB plus C is going to yield, now I'm just going to label these. This is our cation and our anion, and this is a cation, is going to yield, what's going to happen here in single replacement is one of our anions is actually going to switch over to the other cation. So we'll get, on the opposite, on the product side, we'll get A plus CB. Now, some of you might ask, why CB, not BC? Well, because C is our cation, and we always write our cations first. That is called single replacement, because one anion is being replaced and switching over to the other cation. The next one we're going to talk about is double replacement. That's something like AB plus CD. Again, I'm going to label these so you can see it. Cations and anions. Now we have, in double replacement, we have 2 anions. They are going to switch in the products to the other 2, to the other 2 cations. So therefore, we get something like AD plus CB. Those are 3 different types of chemical reactions, chemical equations. Here are your next 2. We have synthesis. So that's going to be A plus B yields AB. Taking small parts, putting them together to make a compound. So that's synthesis. And then the opposite of that is decomposition, where something large, a compound, is broken into its smaller parts, just like you see right here. All right, so that's how all of those are, the 5 major chemical equations work out. Keeping those in the back of your head, we can start attacking how to predict products, because without knowing what type of chemical equation you have, you can't possibly really predict the products. For example, I'll do number 5 on this worksheet. Again, this worksheet is 10.2b. And this says zinc plus silver sulfate yields, you predict it. All right? So zinc, Zn, is always a plus 2. We're just going to keep that right above it right now when it's the charge. It forms an ion of a plus 2 charge, cation. And we're going to add silver. Ag, if you look on your common ion chart, you'll see this is always a +1. Sulfate is SO4 2-. So you can automatically see, if you have your list of chemical reactions down, or if you've memorized it, you can see we have one anion here. That is going to automatically switch to the other cation. So this is a single replacement reaction, hence the single anion. So therefore, on the back side, on your product side, you're going to get zinc. That still has a 2+ charge to it, and SO4, sulfate, which has a 2- charge to it. And you're left off with silver. So I go now, I've done my first step in what I like to say is a 3-step process. I've predicted my products. I've deciphered whatever it is in terms of word formula they give us. I've deciphered that. I've put my charges everywhere, and I've then used that to predict my products. And I still have my charges. That's step 1. Step 2 is to actually go through and bond these things together. And remember, when we're bonding something together, we're trying to get an overall net charge of 0. Well, because that's not bonded to anything, we don't have to really worry about bonding it to anything. It's all by itself. However, we do have silver and sulfate here. Sulfate carries a -2 charge, while silver carries a +1 charge. In order to get an overall charge of 0, I can't reduce this, but I can increase it. I have a -2 from here. This needs to be a +2 in order to actually get a net charge of 0. So what times +1 is +2? 2. That is now a net charge of 0. It's bonded together properly. This isn't a 1-to-1 ratio, so it actually already cancels each other out and makes a net charge of 0. And silver is all by itself. So therefore, that is our bonding. Step 2 is done. Now, I wait until the very end. I'm done with all my bonding to go ahead and erase all of my charges. You do not leave charges in a chemical equation when it's done, because those mean something slightly different. You're working with ions at that point. So here I now move on to step 3. I've deciphered my word formula into an actual chemical formula. I've then bonded all of that, step 2. Step 3 is to balance. So I'm going to go ahead and do this the long, hard way first so you can see how it's done. I put zinc, silver, and sulfate all on my reactant side. I also have zinc, silver, and sulfate on my product side. And I'm just going to go through and see how many of each of these I have on each side. Because the law of conservation of matter, I ultimately have to have even amounts, equal amounts. So 1 zinc on this side, 1 zinc on this side. 2 silvers on this side, 1 silver on this side. So I can actually pop a 2 in front of that, and that balances that out. 1 sulfate, there's 1 sulfate here. I know you see SO4 and you might just think there's 4. No, there are 4 oxygens. I wouldn't pull your polyatomics apart into sulfur and oxygen respectively and try to balance that out. It gets complicated. Don't do that. Leave the sulfate as it is. This is 1 sulfate. On the other side, you also have 1 sulfate. So I just balanced that. You can see the zincs match, the silvers match, the sulfates match. So that one is, I've predicted my products, I've bonded it together, and I've balanced the whole thing. That's number 5 on 10.2b. All right, moving on. I'm going to do number 10. Oh, that's a mess. 10's kind of a mess. If you messed up 10, I get it. I just quickly want to show you 10 is, it says nitrogen plus hydrogen. All right, so I have to predict my products, and I'm going to go ahead and decipher this and write it into an actual chemical formula. Nitrogen plus hydrogen is going to yield something I do not know. Both of these are part of Brinkelhoff. B-R-I-N-C-L-H-O and F. If you see any of those elements all by themselves, not bonded to something, but all by themselves in a chemical equation, you absolutely must put a 2 there. They're naturally occurring diatomic molecules. So therefore, many of you would probably go ahead and slam this together. This is a synthesis reaction, right? So you put something, maybe you did this. Oh, okay, that'd be wrong, but okay. Maybe you did this and you balanced it and you're like, oh, I'm done, great. Okay, I can see where that would make complete and utter sense to do that, but this is, and forgive my ignorance on this one, I forget what the name of this reaction is, but it's very specific. It actually yields NH3. And if you didn't know that right off the top of your head, I completely understand that. Chemistry teachers know that, but chemistry students, beginning chemistry students, do not. So when it comes down to it, I've gone ahead and bonded all this together. Now I'm going to balance it. So I have 2 nitrogens here. I'm going to put a 2 there. And I have 6 hydrogens technically, so I need a 3 in front of that. That is now bonded, balanced, and I've predicted my products and whatnot. I get it. If you messed that one up, a lot of people do. That's not going to show back up again in this course, but it could show up in the future. So in terms of AP Chem or collegiate level chemistry. I'm going to move on to number 16 on this one. 16 says potassium chloride. Plus aluminum oxide. All right, so ultimately, sorry if you can't see that oxide very well. I'll move over a little bit so you can. But I'm going to go ahead and do step 1. I'm going to predict my products. Well, potassium is K, and that has a +1 charge to it. Chlorine has a -1 charge to it when it becomes an ion, therefore chloride. Aluminum is a +3, and oxygen or oxide is a -2. And then I have to predict my products. So when it comes down to it, you can look, there are 2 anions here. This is not going to be combustion. We cannot slam all this stuff together because their charges are the same. So like that potassium and that aluminum are never going to combine together. Well, they may if I put lots of energy to it, but it's not going to happen normally. And so, therefore, it's not synthesis. It's not decomposition. We're not going to break this into its individual parts. So we have single or double replacement to choose from. 2 anions, double replacement. So oxygen is going to bond to chlorine on the, or sorry, to potassium on the other side. So I get a +1 and a -2. The charges follow them. And then aluminum is going to bond to chlorine. That's a +3 and a -1. So I've now done step 1. I am now going to go through and bond these things together. So I have a 1-to-1 ratio here. That's done. I have a 3-to-2 ratio here. 3 and 2 don't go into each other except at your least common multiple, which is 6. So ultimately, I need a -6 and a +6 in order to get my net charge of 0. You can also do this little switcheroo. We've talked about that in classes before, where you just kind of switch them. And you can do that with all of these when you really think about it. But people get stuck on 3 and 2 for some reason, so that's the one that's most common. That means that the 2 goes here with aluminum and a 3 goes here with oxygen. If you wanted to check yourself before you wreck yourself, look at it. 3 times -2 is -6. 2 times +3 is +6. That gives me a net charge of 0. I've done that correctly. This is going to be a 2 right here. 2 times +1 is +2, which cancels out your -2. And then I need a 3, and I don't know if you guys can see that. Yep, you can. A 3 on the chlorine. 3 times -1 is -3. 1 times +3 is +3, which gives me an overall net charge of 0. My bonding is done. Now I'm going to go through and balance. But first I'm going to erase all of my charges, because we do not keep charges in a chemical equation unless we're talking about an ionic equation, which we're not. So now I have 1 potassium here. I'm going to do this a little bit faster this time. 1 potassium here, 2 potassiums here. I can go ahead and pop a 2 right in front of that. That actually affects my chlorine now. Now I have 2 chlorines on my reactant side. On my product side, I have 3. 2 and 3, not going to go into each other right away. So for ease, I'm just going to skip it. I'll skip chlorine. Let's move on to aluminum. I got 2 aluminums on my reactant side, 1 aluminum on my product side. So I'm going to put a 2 in front of that. That balances my aluminum, and that just opened up my chlorine technically. On this side, I now have 6 chlorines, which I would have to change this to, hence why we use pencil in chemistry, into a 6. All right, that just messed up my potassiums, but I can pop a 3 right here in front of that. 6 potassium, 6 potassium. 2 aluminums, 2 aluminums. 6 chlorines, 6 chlorine. What's left is oxygen, 3 oxygen, 3 oxygen. So that is now bonded and balanced, number 16. All right, let's do another one. I'm actually going to do a combustion reaction because we don't see those very often. We see a lot of double replacement, single replacement reactions, but we don't see a lot of combustion reactions to go ahead and predict your products and bond and balance and all whatnot. So I'm actually going to say tricarbon octahydride plus oxygen yields who knows. All right, so this is covalent bonding now. We see the tri and the octa, and you have to know that's automatically covalent bonding. So tricarbon, that's C3 octahydride, H8. In layman's terms, this is propane, but in chemistry, tricarbon octahydride plus oxygen is going to yield, now, 2 things. First thing, that oxygen is all by itself. Remember, it's part of Brinkelhoff. We need a 2 there. Now, when you see this, automatically you got to think carbon something, hydrogen something plus oxygen. That's combustion. And you already know your products. You don't have to do the weird bonding that we've been doing before. It's H2O and CO2. Always, forever. You could have put CO2 here and H2O there. It doesn't matter. They're products. You can flip-flop them, all right, as long as they stick together on the product side and you have H2O and CO2. So there, we have now technically already bonded it. Now we have to balance it, all right? So balancing comes down to 3 carbons, 1 carbon. So I'm going to pop a 3 in front of that. I like to leave my hydrogens for absolute last when it comes to balancing, just because it makes life a lot easier for me personally. I'll use it if I have to. Like, let's say I can't balance this oxygen right now because of something. Then I go ahead and skip the oxygen and move on to hydrogen, and that sometimes helps me out. But I'm going to leave it to last if I can. So I'm going to skip it and go oxygen. 2 oxygens here and 6, 7. 2 and 7 are not going to go into each other. So here's the perfect example of where I actually have to use hydrogen, not last, to bond. 8 hydrogens here, 2 hydrogens here. I'm going to go ahead and pop a 4 in front of that. That gives me 8 hydrogens and 8 hydrogens. And that just messed with my oxygens. So now that I can potentially bond my oxygens a little bit better. So my carbon's taken care of, my hydrogen's taken care of. I got 2 oxygens over here, and 4 plus 6 is 10. 10 oxygens here. What times 10? What times 2 is 10? 5. So 10 oxygens, 10 oxygens. That is a combustion reaction. All right, those ones are actually a little more simple, even though a lot of us consider them to be hard to memorize. They're simpler to bond and balance. All right, and then I'm going to do the hardest one, which is, well, one of the hardest ones, which is number 25. This has an acid in it. It says hydrogen sulfuric acid plus iron 2 chloride. Okay? This gives people problems. The reason why it gives people problems is because most people are not super solid with their acid naming rules. I like to actually, I didn't do it. One of my students did it, and I use it. I'm stealing it forever. The acid naming rules is technically hydroic was IDE, I-D-E, and then 8 turns into OUS, so OUS would have been 8, and then, no, Sprite. OUS is ITE. See, I even struggle at acid naming rules. ITE goes to OUS, and then 8 goes to IC all by itself. Let me show you what this means. And if you have your common ion chart, look at the bottom of your common ion chart. It's actually there for you. One of my students told me a long time ago, my ride has hydraulics. That means IDE turns into hydro blank ic acid. I thought my ride has hydraulics. That's a great way to remember it. Everyone uses the Sprite is delicious. That means ITE turns into OUS. And then my last one, some people use this as well. I ate something icky. I probably didn't spell that right. Nope, I did not. But it makes sense. Okay. So 8 turns into ick. That's how a lot of people memorize them. So given that my ride has hydraulics, Sprite is delicious, I ate something icky, work backwards. We already have the acid name. Hydroic. Well, hydroic acid used to be IDE. Well, this is hydrosulfuric. So that used to be sulfide. So if that was sulfide, and we know that all acids start with hydrogen, then we can combine these two. That's a +1, that's a -2. That means we need H2S, hydrosulfuric acid, plus iron 2 chloride, iron 2 chloride. All right, I probably shouldn't have done that. That confused some of you because I skipped a step, but that's the way it bounces out. So now, I'm just going to go ahead and erase that. It bothers me too. Now I need to predict my products. You can see you have 2 anions here. 2 anions, double replacement reaction. So therefore, my sulfur is going to bond to my iron. This is a +2, so -2. And my hydrogen bonds to, can you even see that? Yep, you can still see that. My hydrogen bonds to my chlorine. Sorry that that's squished over there, but I was running out of room on the screen. All right, now I can go ahead and do what I was started to do before, which is bond these things together. Technically, this is a 2. 2 times +1 is +2. 1 times -2 is -2. That cancels out, equals net charge of 0. I'm going to go ahead and put a 2 here for the exact same reason. I need a -2. This isn't a 1-to-1, and this isn't a 1-to-1, so we're solid there. Now this is all done, and I need to erase my charges and balance this. 2 hydrogens here, 1 hydrogen here. Okay, sorry for the ugly 2. 1 sulfur here, 1 sulfur here. 1 iron here, 1 iron here. 2 chlorines here. Oh, look at that. 2 chlorines there. I am now balanced. So I've done a couple problems up here. The synthesis problems can be a little weird from time to time, depending on how that synthesis reaction works. This is really common problems you guys are going to see over and over again are single replacement, double replacement. And so I've covered a majority of them here. I also did the combustion. Decomposition is literally just something large being broken apart into its individual pieces. So that shouldn't be too tough for you. Hopefully this helps. Watch this video as many times as you need to in order for it to help. And if you have any further questions on it, please bring them up in class as soon as you can. Don't comment on this video because, well, I won't be reading your comments. I'll probably end up disabling the comment section anyway. But I'll take questions in class. Thanks so much, everyone, and good luck.